Hello friends, welcome back to my channel, a physicist Buddhist in California. So today I'm going to talk about in detail about a textbook, a famous textbook of quantum mechanics. I posted a brief video about this book a while back, so today I'm going to talk in a little bit more detail. So the book is called Quantum Mechanics by Leonard Schiff. So let me show you so you can see. Okay, and so this happens to be the first original edition of this book, which came out in 1948. So this is a classic book, one of the greatest textbooks of quantum mechanics ever published in any language. So a little bit of history before I start on the book itself. Leonard Schiff was a great physicist of 20th century, and he was also a student of Robert Oppenheimer at University of California at Berkeley. So at UC Berkeley, Oppenheimer used to give lectures on quantum mechanics, and Leonard Schiff was one of the students in his class, and he took notes. So this book basically grew out of those notes that Schiff took in Oppenheimer's lectures at UC Berkeley. So you could say that the genesis of this book lies in the lectures that Oppenheimer gave in early 40s at UC Berkeley. Okay, so this was the standard textbook of 20th century for quantum mechanics. I used this book when I took classes in quantum mechanics when I was a graduate student at Michigan Technological University, and by then this book was more than 40 years old, but we still used it and it was useful. So let's talk about what this book actually covers. So after a brief history of quantum mechanics, the birth of quantum mechanics in Europe in 1920s, Schiff talks about the fundamental ideas about quantum mechanics, and the foundation of quantum mechanics is Heisenberg's uncertainty principle. So he talks about that, how Heisenberg's uncertainty principle comes about, how it shows us a whole new world which is very different from the classical world in which we live. So how the quantum world differs from the classical world, it's determined solely by Heisenberg's uncertainty principle. So we could say if the uncertainty principle applies, then the object we are studying must be in the quantum world. If it doesn't apply, then it's in the classical world. When I say it doesn't, it's not strictly speaking that it does not apply at all. It's not relevant because it applies everywhere. It's a universal principle. But for the classical world, the world of everyday motor cars and baseball and people, we can safely ignore the implications of uncertainty principle. But when we talk about the world of molecules, atoms, electrons, protons, quarks, then of course they are solely governed by Heisenberg's uncertainty principle. Now we'll talk about what this book actually covers. Like I said, after talking a little bit about the history, he starts to talk about the uncertainty principle, and then he goes on to the Schrodinger's wave equation, which is the workhorse of quantum mechanics, non-relativistic quantum mechanics. So if the electron or the quantum objects are not moving at close to speed of light, then we don't need to worry about relativistic effects, and so we can use Schrodinger's wave equation, which is the non-relativistic equation that's used to study quantum objects. So Schiff goes about this in great detail. He shows us how to solve Schrodinger's wave equation for certain cases where an exact solution is possible. For example, for spherical symmetry, it can be solved exactly for hydrogen atom, which happens to have only one electron, and in fact that's the only place this equation can be solved exactly. So Schiff shows how to apply Schrodinger's wave equation to hydrogen atom and to obtain exact solution in spherical coordinates, and so how we can then calculate the the eigenvalues and the eigenfunctions corresponding to those eigenvalues for hydrogen atom. And from there he moves on to more complex atoms, like for example helium, where the equation cannot be solved, so one needs some approximation methods. And so most popular approximation methods are variational methods and WKB. So he talks about that, and then he talks about the problems in quantum scattering or quantum tunneling, where yet another method is useful, quantum perturbation theory. So that, and then he talks about the time independent perturbation theory and time dependent perturbation theory. And after covering all these topics, then he talks about collection of quantum objects. So then these objects could be either of one type or the other. One type is fermion, where each quantum object has a distinct identity, which means that no two fermions can have all the quantum numbers which are identical, so they should at least have to differ in one quantum number in respect to one. So for example, an electron in a hydrogen atom has a unique set of 4 quantum numbers. These are principal quantum number, angular momentum quantum number, magnetic moment quantum number, and spin quantum number. So no two electrons can have all 4 same quantum numbers. So even if there are 2 electrons in the same orbital, they must differ at least in one quantum number, which is the spin. So if one electron has spin up, the other one would have spin down, and that's how they can occupy the same orbital. Okay, and then he talks about identical particles, which are called bosons. So example is photon. A light photon is a boson, which means that now for bosons, the idea that applies to fermions, it doesn't apply, which means that they don't obey the Pauli exclusion principle. So 2 bosons, 3, 10,000 bosons can occupy the same quantum level, and so he talks about that. So then Schiff moves on to much more difficult topics which are more current in the sense. So he talks about the quantum object which is moving with a relativistic velocity. So there he takes us to a relativistic quantum particle mechanics, and the standard workhorse there is Dirac's equation after the famous physicist Paul Dirac. So he talks about Dirac's equation to apply it to a relativistic electron, and that's where the idea of spin comes in. So that's where the idea of electron spin comes in. So in order to understand the spin of an electron, one has to treat the electron as a relativistic particle, which means, strictly speaking, Schrodinger's wave equation, which is applied to a hydrogen atom, it does not explain the spin of the particle. So basically it explains hydrogen atom's electron as a spin 0 particle, which is kind of a paradox in terms, because electron has a spin half. So if it has a spin half, it must be a fermion, because if it has spin 0, then it's not a fermion, it's a boson. But in Schrodinger's wave equation, the spin is added by hand, so we add the spin at the end. After doing the calculation, we add the spin by hand. But in Dirac's equation, the spin is right up front and centered, so we don't have to add the spin, because the equation itself gives us the spin at the end. So in order to do a clear and scientifically correct explanation of an electron which has a spin, one must use Dirac's equation. So Dirac's equation, it basically takes the Schrodinger's equation and it adds relativistic motion of the electron. It takes that into account, and as a result of that, we get many wonderful things like the spin I talked about. And not only that, Dirac's equation also predicts the existence of antiparticle. This was one of the greatest achievements of Dirac's equation, that it predicted the existence of a state of matter which nobody had ever predicted before, antimatter. So for every matter particle, there is an antimatter partner. So for example, for electron, it's called a positron. So what is the difference between an electron and a positron? They are identical in every way except they have opposite charge. So electron has a negative charge, it has a spin 1/2, it has a mass. Same thing true, positron has exactly the same mass, it has the same spin, but the sign of the charge on a positron is exactly opposite Positron is the antimatter partner of electron, which is identical to electron except that it has a positive charge instead of negative charge. And what happens, and this is a very wonderful part of antimatter, when matter and antimatter meet, they annihilate, and the total mass of the electron and positron is converted into 2 gamma ray photons. So the mass of an electron is 0.5, approximately 0.5 million electron volts, and the mass of positron is also identical, 0.5 million electron volts. So they emit 2 gamma ray photons whose total energy adds up to 1.1 million electron volts. So the masses are a little bit higher than, that's why it adds up to 1.1. So this is how this whole idea, and this whole idea comes out of Dirac's equation. This was the result of Dirac's genius, that his equation not only predicted the existence of spin, it also predicted something which was completely unexpected, the existence of antimatter. Okay, so after talking about Dirac's equation and how to solve it for hydrogen atom for spherical symmetry, again Dirac equation can also be solved exactly just like Schrodinger's wave equation can be solved. Of course, Schrodinger's wave equation, like I mentioned earlier, it's non-relativistic, and Dirac's equation is relativistic. So one is moving with a slower velocity, and the other one is moving with much faster velocity. So the Einstein's special theory of relativity, that becomes important when you take into account the relativistic. So in Dirac's equation, it's basically a perfect marriage of quantum mechanics and Einstein's special theory of relativity. Okay, so that's Dirac's equation, and after that he goes on to more advanced topics. He lays the foundation of quantization of quantum fields, or the idea of quantum field. So basically the most fundamental idea in physics now is the idea of quantum field. So this whole lecture series is about quantum fields. So the idea, like I talked about earlier, is that the quantum field is the most fundamental object in the universe. And so for example, let's take electron. So there is a quantum field of electron that permeates the universe. Every single space-time point is permeated by this quantum field. It came into existence when the universe was born, and as the universe has expanded, the quantum field has expanded with it. So, and every single electron that we see in the universe is a quantized excitation of this quantum field. So of course, the word quantum means that these fields, they are all quantized, which means they can have only discrete levels of energy. So this is what Schiff now talks about. So he starts with the electromagnetic field. So electromagnetic field is another example of a quantum field. So the light we see, it's a result of that quantum field, the excitation of that quantum field. So he talks about how to quantize the electromagnetic field, and then he moves on to the quantization of the electron field, and in the end everything has to come together. So a quantum field of light or photon and the quantum field of electron are interacting with each other, which leads to one of the fundamental theories of nature, what's known as quantum electrodynamics. So quantum electrodynamics is the quantum field theory of a quantum electron interacting with a quantum photon. So this book was published in 1948, and at that time the quantum electrodynamics was still being developed. So it was not finished, and physicists were not really sure how this theory is going to pan out. There were severe problems with it because the theory used to give answers which made no sense. It gave infinities. So those problems were resolved shortly after this book was published in 1949. So in this first edition, that's where Schiff stops. So he lays the foundation of the problem, and he describes what the problem is, and then he also mentions that, okay, this is still an open problem. It was then, but it's not now. So shortly after this book was published, a very famous physicist, Richard Feynman, I'm sure you have all heard of his name. He was one of the 3 people who actually solved this problem completely. So the quantum electrodynamics then appeared as a finished theory of quantum interaction of a quantum electron with a quantum photon, and what happens when these 2 quantum fields interact with each other, giving rise to this theory known as quantum electrodynamics. So I would stop here. Thanks for your time, and I hope you enjoyed this lecture. If you have any questions, please mention below, and near future I'll post more lectures on different areas of quantum field theory. Okay, see you then. Thank you.